we're back for last two problems here, and I just went through about half of this, and my software just stopped working, so I had to start over. So big fun for that. All right, so this little piece just sort of speaks to the fact that this is one option for half-life if you memorize this formula. Okay, and under the time here is where you put the half-life. The base is half, and whatever that number is that every substance has in terms of decay goes here. Or you can always use, your A equals A sub 0, your exponential law of change, KT, but here you put the half-life in at time. So I just want to make that clarification. That's kind of what this is speaking to. This just kind of wants you to realize that I think this is worded sort of weird. This is just saying, hey, you got this formula or this formula. If you remember this, use that. If you don't, you can always depend on your PERT formula. Okay, so I'm going to solve the next problem with both of those so you can see. And I don't want you to get confused, on a test if because you have to put that half-life in different places. So this just says, for each method. All right, so each radioactive substance has its own half-life. It's a constant. All right, and so it depends only on whatever substance it is, not on the nuclei or amount present. Sorry, nuclei is right there. Not on the amount present at the beginning, or it just depends on that half-life. Okay, so this says that we have a half-life of 1,600. What do we have? Radium, 1,600 years. Okay, so find a formula, and when will it be 20? So I'm going to kind of do A and B for both methods here, so you can kind of see what I was talking about. Let's use the easy method first. That the amount will be the initial half-life time over that n, and so that n again is going to be that 1,600. So we're looking for when will it be 20? Solving for time, and 1,600 goes in here for n, which would it's going to be the k over here. All right, so 2 over 5, which I'm recording, 1 half t 1,600 ln 2 over 5. Pull down the exponent, ln 1 half. Divide. Let's just clean it out. So 1,600 times ln of 2 over 5 divided by ln of 1 half is t. All right. So calculator magic. Okay, go to your TI, 1,600 times ln of 2 over 5. Okay. I think too many parentheses here. No. Okay, divided by ln of 0.5. Okay, so we've got 2,115, we'll just round it years. Well, we'll be like the AP exam, 0.085. Did it say to the nearest year? Equals time. Years, don't forget your units. All right. Okay, so that would be knowing this half-life formula method, which again is derived from the other method. We've spoken to that. If you used the PERT, law of change PERT, if you will, you'd start here, KT. Okay, and so this one we have to figure out the K. So on this one we have to go with, this one is not as ideal because we have to figure out the K. So we'd have to go with, let's just use, 1.5. We could use A sub 0, and what's the amount here? 1 half A sub 0, and I could mark through the A sub 0s, but let's just use 1.5. A hypothetical, started with 1, we ended up with 1 half e to the kt. And so now we're using, when will we have half? 1,600. Okay, so that's why this is confusing, because here it goes into the 1,600, goes into time, but in this one it actually goes in as kind of that k value, that half-life value. All right, so this is ln of 1 half equals 1,600k, ln of e gone. So k here is ln of 1 half over time. Okay, so we're going to go and solve the problem when we have 20, starting with 50, e to the ln of 1/2, 1600 t. So 2/5 equals e to the ln of 1/2 over 1600 t, ln of both sides. Okay, and so that's going to pull that exponent down, all right? And let's see, ln of 1/2 for 1600 t, ln of e. All right, and so you can see exactly what's going to go on here. I'm going to get ln of 2/5 times 1600 divided by ln of 1/2, which looks extremely familiar to this. So hopefully you can see the similarities between the two, because essentially they are the same thing. All right. And so we'll get 2115.085 years. Okay, so either way you want to solve both of those problems. If you're asked to give a formula and you gave this formula, great. If you're asked to give a formula and you gave this formula, great. They're the same thing. Okay, Newton's law of cooling. All right, so this is not exponential change. This is a new law, and they added this into the AP exam like 5 years ago. So Newton's law of cooling. All right, Newton's law of cooling states that the rate at which an object cools or warms, okay, is proportional to, so that's like a constant of variation is going to come in, to the difference in temperature between the object and the surrounding medium. So surrounding air, that is. A glass of juice is taken out of a 40-degree Fahrenheit refrigerator, I assume, and placed in a 65-degree Fahrenheit room. If the juice warms to a temperature of 50 degrees Fahrenheit in an hour, how long will it take it to warm to 60? Okay. All right, let's write the formula first. Okay, so the change is proportional to the rate at which it cools is proportional to the difference in temperature of the object and the surrounding medium. So when you say difference, the word that's mentioned first comes first, and this is just the temperature in the room. Surrounding medium means the temperature in the room. All right, so a glass of juice is taken out of 40 degrees. So at time 0, it's sitting in a 40-degree icebox, refrigerator, what have you. So the initial temperature is 40, and then it's going to be placed in a 65-degree room. So that's your T surrounding. Okay, that's your T surrounding. And then in 1 hour, it's 50 degrees, the juice. And in how much time will it be 60? I think this was on the AP exam like 5 years ago. It's a potato problem, potato cooling, I think. And oh my goodness, the next day after the exam, this is smaller, the potato problem. So that was on the AP exam, I don't know, one of those years. And all of those past exams are out there. Google any free response. The multiple choice is not, but all of the free responses from years past are everywhere on the internet. So there's tons of places for you to practice in all of your extra time. Okay, so let's see what we can do with this formula. Let's separate those variables. Okay. All right, so we are going to get, I've written this in T, so I'm going to need to write this in T, so that'll help. All right. Okay, so we're talking about time and temperature. So input of time, output of temperature. So Y is your output variable, but we're using, temperature here. So, and, as the exponential law of change, written with the Y variable over here. the amount present, if you will, but now it's temperature and it's a difference. So it's not the law of exponential change, but the dependent variable being involved. Okay, so this is 1 over T minus T surrounding dt equaling to K dt. So this is time and this is temperature. So integrate. All right, so ln equals kt plus c. Exponentiate. Split. Absolute value assessment, plus or minus. Let. Okay. So we're going to say T equals C E KT. So it looks a lot like PERT, so I wanted to show you that. But we're just adding in this T S here. Adding in this TS here. All right, so let's solve for C with our initial. Okay, so we're going to get 40 equals C e to the K 0 plus 65. So I wanted to show you this because if you have to deal with Newton's law of cooling, just remember our kind of PERT, which helps us out, and just add in T surrounding. It's just PERT, add in T surrounding. Okay. So this is going to zero out. So C here is going to be negative 25. All right. So we're going to use this to find C. We're going to use this to find K, and then we're going to solve. T, okay, T equals negative 25 e to the K T plus 65. All right, so let's use our second data point, 50 degrees, negative 25 e to the K times 1 plus 65. Okay, so negative 15 equals negative 25 e to the K. 15 over 25 equals e to the K. So ln, let's go ahead and do, 5 goes into there, 3/5. K, ln of e. Boom, there's your K. Okay, so check, and ready to solve the problem. When will it be 60? Okay, so we are starting out with our C value. Well, not starting out, but here's our C value. E, K is now ln of 3/5. All right, ln of 3/5. And we've got our T for when, and plus our surrounding. So not too hard to memorize Newton's, just same song and dance, just add in that surrounding. All right, you can go for it from here, or you can, clean this up if you want to drop the 3/5 and do that, which is what I like to do, but you don't have to, so it's kind of up to you. So I'm going to move the 65 over and get negative 5, and I'm going to cancel, drop to the T. All right, this is going to be 1/5 equals 3/5 to the T. And you could log it now or ln it. The E's gone, but we'll just stick with ln. And there we are. Okay, let's see what we get. Math is fun and easy. All right, there we go. hours, 3.15, 1 hours. Okay, which would be 0.151 times 60. 3 hours, 9 minutes, and 3.6 seconds. That's as good as I can do. All right, guys. There you go. We're done with chapter 7. We will see you back in class. All right. Have a good one.